Hello, welcome to our fourth video on differentiation, and today we're going to be covering some differential equations problems. So this looks pretty tame at first glance just because the problem is short, but it can get confusing, especially part D. So part B, we have to find the second derivative in terms of x and y, and okay, we've got to also determine the concavity. So let's first start by differentiating both sides of this, right? So when you differentiate the first derivative, you're going to get the second derivative. And then over here, the derivative of x with respect to x. So I'm going to write it like this, d by dx x minus d by dx y, because this is really what we are doing when we're differentiating both sides. So the derivative of x with respect to x is just going to be 1, right? Because that's the slope of the line y equals x, right? Just graph this here, right? Slope is always going to be 1. And then the derivative with respect to x of y is actually going to be dy dx, right? Because you have to keep in mind that y is a function of x. That's why they put dy on the top and dx on the bottom, right? It implies that x is a function, y is a function of x. So yeah, this step you may not want to write out, and this was what you write out. So you're going to get 2 minus dy dx. Now they want us to express it in terms of x and y, so let's just plug in whatever we have here for dy dx. 2 minus 2x plus y. Okay, so there we have it. Pretty simple. This next part may not be so simple, so we've got to determine the concavity also. So first we've got to employ our previous math knowledge. So where's quadrant 2? That's right there. So what do we notice about coordinates inside quadrant 2? So typically the x-coordinate is negative, right? So I'm going to write x is less than 0, and also the y-coordinate is positive, so I'm going to write y is greater than 0. Okay, so we know these two things, and we're trying to figure out the concavity. So what really is the concavity, first of all? It's really, we're trying to figure out what the sign is of the second derivative, right? Because that will determine the concavity. If it is positive, then we know it is concave up, so it might look something like this. In quadrant 2, that is. And if it's negative, then we know it's concave down, so it can look something like this, right? So concave up, concave down. So, okay, how can we figure out whether this is positive or negative? Well, we know that x is less than 0 and y is greater than 0. Let's keep it concrete here and plug in a specific value for x and y. I think this is a great tool in helping you figure out patterns, general patterns for all x and y in this case. So maybe we'll plug in some easy number like -1 for x. So plug in -1 for x, and y is greater than 0, so let's use 1. Okay, so let's plug in this point in here, see what we get. So we're getting 2 minus 2, and then the -1 plus 1. Okay, and then these minuses are going to cancel. That's an important observation. So it's going to be +2 plus 1, and we will just end up getting 5. Okay, so now the value that we got here isn't super important, right? It's that it's greater than 0. That's what's important. And in general, if you're going to have any x value that's less than 0, right, you're going to have 2 minus 2 times some negative number, right? What's going to happen is these minuses are always going to cancel out, so to speak, and you'll get 2 plus 2 times some sort of positive number, right? So this expression is definitely greater than 0, right? And we're just adding 1 to it, so that, yeah, you know, oh, well, we're adding y to it, but the thing is that y is greater than 0. So yeah, of course, right, we're adding another positive number. So, well, yeah, this is also going to be positive. This is going to be greater than 0. So yeah, this, we know that the second derivative will always be positive, and so we know that we're going to be concave up in quadrant 2. Right, and the reason that you would give is, right, you would say that this second derivative is greater than 0 when x is less than 0 and y is greater than 0. Okay, great. Now we've got to do part D, which may not be as obvious. So let's read this here. So find the value of the constants m and b for which that is the solution. So let's just write down, right? Always a good idea to write stuff down that they give you. And then I'm going to just write down this differential equation too, because they mentioned the differential equation in that sentence, so that's probably worth writing down. Okay, and we just want to find what m and b are. So what's a good idea to do? Well, we have a few options, right? We could differentiate this side, right? Maybe if we differentiate, we'll get a dy dx, and that equals mx. So m is just a constant, right? So when you're differentiating mx, you'll get m, right? Like when you're differentiating 2x, you'll get 2. When you differentiate, I don't know, 4x, you'll also get 4. And so like that, we're just replacing m is some constant m, and then it's just going to be m. Okay. And they give you 1 point for writing this down. So, and maybe the reason why they do that is because it might not be entirely obvious, given that you're differentiating some like variables instead of or some letters at least. This isn't technically a variable, it's a constant. And then this b, right, is another constant. So the derivative of that is just going to be 0, because the derivative of a constant is always 0. So you'll just end up getting m. Okay, so now it is natural for us to compare these two, right? So you go m equals 2x minus y. And now remember, we want something in the form of y equals mx plus b, right? So in this case, well, okay, why don't we wrangle it into some form like that by solving for y? So y minus 2x, I'm going to rotate this now, so 2x minus m. Okay, so now here is where things might get confusing. We're going to compare it with this, y equals mx plus b. Now you have to realize that this m and this m are actually exactly the same m, and you also have to realize that this comparison is also like valid. You can compare these terms, right? Because they're exactly in the same form. So you know that m has to be 2, right? Because well, you're just comparing this term right here. So maybe you can write this as mx has to be equal to x, right? So m has to equal 2. Okay, and the other thing is that these two have to be the same, right? Because remember, this is the same line that we're talking here. And y equals mx plus b is the same as whatever this we're getting. So we know that minus m has to also equal b, right? Because we're just comparing this term right here, right? So now if we plug in a 2 for m, we get b is minus 2. And we can stop right here, right? We're pretty much done. You can write out the line if you want. So 2x minus 2. Right? But they only ask you to find, well, m and b. So really you're done after you just find m and b. Now, if this solution was a little confusing to you, maybe a different way to do the problem is to just plug in the value of y. So we have dy dx is m, and we also have dy dx equals 2x minus y. So we're gonna leverage the fact that dy dx is m, right? But then when we write y, we're not gonna write y, we're gonna write mx plus b. Because that's what it is, right? We're trying to find some y equals mx plus b. So now we're going to just distribute, right? It's a minus 1. And now it might not be immediately clear how to do this. This is why I sort of put this solution second, because I think it's a little less intuitive, personally. But we're going to subtract m from both sides. Minus mx, minus b, and minus m. And now we're going to employ a similar tactic of comparison of terms, but in order to do that, we're going to factor out an x here. So it's going to be x multiplied by 2 minus m, right? And then we're going to add right? We're adding some b, so I'm just going to add for simplicity, and that's going to be minus b minus m, right? So now what? Well, we know that this expression has to be 0, and so this and this have to be 0, right? Because this has an x in it, so this has to hold true for all x, and the only way for that to happen is if this is 0, and then if that part is 0, then that one also has to be 0, right? You can't have a situation where they somehow, like, this is minus 3 and this is 3, because then it's not true for all x. You have to make sure that this is 0. And how do you ensure that? Well, 2 minus m is 0, right? And then after that, it becomes a lot easier. So then minus b minus m is 0. And you get pretty much the same thing. So 2 is m, minus b is m, plug in, and then subtract. I mean, multiply with minus 1. And we get exactly the same values for m, b. So, yeah, that was it for this problem. This is a somewhat niche problem on the AP exam, but it is one that is sort of hard to do without first seeing it. So I wanted to bring it up in this video just so that if you encounter a similar problem, it's going to be a lot easier for you since you've already encountered it once. Alright, I hope this video was helpful, and I'll see you guys in the next one.